that Steve mentioned earlier about building models to support control or to support reinforcement learning. So we can actually use these generative models to actually, learn from data to build a generative model, the dynamics to learn the dynamics of the scene or of the environment, and then to use that model in the context of reinforcement learning to train a good policy. Right. So this is another area where generative models are being used currently. And finally, this is the one where sometimes it is just about pretty pictures. Let's imagine you have a low-res image and you want to create a high-res image from that, but the data is lost. You don't have the high-res image, right? So all you have is a sense that this is maybe grass, right? So you can actually use a generative model to imagine extra details in there. And it's important to realize that these details are not the details that would have come from the original image, right? Those are lost forever, but it's inventing details that are somehow representative of the real data. So you can imagine doing this with a movie, right? You could take a movie, compress it down to a tiny number of bits, and then expand it using a generative model while you watch it. And the fun thing about that is that it will be slightly different every time you watch it, right? Because subtle things will be different. There'll be a tree swaying, and maybe the branches and the leaves will be in different places. But this is the kind of thing you could really imagine doing with these models. So those are the kinds of motivations that I have for generative modeling. These days, the most strong motivation I have, but it's for a very specific kind of generative model, is looking at sim to real, right? So this is a case where you have, this is another application inspired by reinforcement learning, actually, where you have some simulation environment that is a pretty poor representation of the real world. And you want to train a robot in this simulation environment because it's a lot easier to train it in simulation than to train it in the real world because the amount of hours it would take to actually do that doesn't make it practical. But what you want to do is, usually the way this is set up right now, the policies that are trained in simulation don't transfer well to the real world because they're just, the simulation isn't close enough. It's not close enough to the real world scenario. But we can collect data from the real world and we can augment the simulation with this generative model collected on the real world. So we can render that simulation much more realistic. So I think this is a really exciting application of these models, and that's an area where I've been looking more specifically myself. But on the topic of just general generative models again, we can think of these things as basically breaking down into two different types of generative models. And at least for our purpose in the couple of lectures I'll be giving, they break down this way. So on the left here, we have autoregressive models. And I'll be talking about these first. Now in this case, this basic strategy is here. We're gonna model the structure within data by breaking it down and modeling components based on other components, right? So in this case, we're imagining modeling data that exists in 5 dimensions, x1 through 5. And we're just going to have a simple model of x1 here. And then we're going to generate x2 based on the value of x1 that we generated in the first instance. And then we go on and we model x3 conditional on a value of x2 and the value of x1, et cetera. Right? So this is a basic way we can do generative modeling. And we can use neural nets to sort of parameterize these arcs to get fairly complicated and rich interactions between these values. And I'm going to show you different ways we can do this shortly. The other kind of model that I'm really going to spend most of my time on are what we call latent variable models. And these models are actually very close to my heart. And the basic idea here is that we have some latent variable z that we imagine it has some simple distribution, right? And that we have some possibly very complicated transformation that's going to be parameterized, in our case, by a neural net that transform this simple distribution into a very complicated distribution in the data space. Right? And there's all different kinds of ways we can do that, and we'll be going over 3 of the main ones. And I basically am having trouble imagining something that I would consider to be a deep generative model that doesn't fall into either one of those 2 camps or use elements of both of these. We're actually going to see an example later on, if I have time at the end, that uses these kinds of pieces in conjunction with a basic latent variable model. Yeah. All right, so this is an outline of the kinds of models I'll be talking about. I'm going to start with autoregressive models. Specifically, I'm going to be talking about pixel CNN. I'm actually going to introduce this by way of NADE. Yeah, question?
Are there any generative models that are undirected graphs?
Oh yeah, I'm sorry. Yes, absolutely, there is. Okay, there's a very long conversation to have about that. Yes, yeah, good point. Okay, so this is a directed graphical model, right? And what makes it a directed graphical model is I've added little arrow ends here, right? In these cases, sampling is straightforward. You sample Z. We've specified it some simple prior. That usually means something we can sample from. And then we just push that sample through, and we get a sample in the latent variable space here. So this is, and with these directed graphical models, that's usually the sampling procedure. Now, there's a whole class of undirected graphical model that I've neglected, and thanks for bringing this up, where you're modeling, usually the way these things work, and you're modeling an energy function. And they can have structure as well, but the structure is usually defined by an energy function. And they can also have latent variables. So you can have terms in the energy function between the different elements of X, but also between a latent variable and X. So if you've ever heard of a restricted Boltzmann machine, this very much fits into this category. I'm not going to be talking about those today, mainly because I'm going to be talking about, I think, what I would term sort of more recent innovations than models like restricted Boltzmann machines. In my own research, back a few years ago, I worked very heavily in those kinds of models, Boltzmann machines and restricted Boltzmann machines. I've since moved on to different kinds of models. We can go into more detail on that if you're interested, on why I think those models don't lend themselves very well to high-dimensional data such as images and things like that. I have an opinion on that, but yeah, we can go into that if you're interested later. All right, so overview. I'll be talking about Pixel CNN and WaveNet, which is kind of an application of models like Pixel CNN to speech and kind of waveform type data. And then I'll be getting into the latent variable models. I'll be talking about normalizing flows. Then I'll be talking about variational autoencoders. And then that'll be it for today. And then tomorrow I'm going to pick it up again with a whole lecture on generative adversarial networks and extensions of that model type. All right, so, oh yeah, one more thing. Something that I won't be speaking about is what actually, ironically, is probably the most successful application of generative models to date, which is in language modeling. Right, so language models are very successful, and there's been a tremendous amount of research in this topic recently. I'm not going to talk about it simply because that would take up an enormous amount of time, and it's a topic all on its own. So I'm just going to ignore that for now, put it off to the side. But it is a super interesting area. I highly recommend you go and look at the recent innovations, especially that have happened in this field. And what's really special is that those kinds of generative models, those language models that are out there now, are really driving the state of the art in NLP. Which is not really true on the image side. The generative models are not necessarily driving state-of-the-art, at the forefront of things like ImageNet classification, right? These are usually just purely discriminative methods and not really using the generative models. But in language, that's not the case. And I'll also talk a little bit about speech, as I said, WaveNet, and I'm not going to be talking about music generation at all, which there's also been a lot of really interesting, exciting work in that field. So if I want to describe a kind of a dichotomy of what generative models exist, actually, so here are the restricted Boltzmann machines that we mentioned earlier. They sort of fit under here, where you're doing an explicit density modeling, but you're using an approximate density application. You're approximating the density, and the approximations usually have to do with the fact that this formalism has something called a partition function. Right, which is the thing that allows you to normalize these big joint probability distributions. And you have to normalize those. So, and GANs we find over here. GANs we term an implicit density because of those two types that I showed you before, where one is you're explicitly doing density estimation, and the other, you're just trying to generate samples that look like the training distribution. GANs fit into that category. So that's why they're over here in the implicit density distribution. So today we'll be focusing on this category here, right? So explicit density models. So we're almost always going to, well, basically we're always going to be doing maximum likelihood training, right? That is the probabilistic formalism that we'll be using, right? So we're going to collect some data samples and we're going to try to maximize the likelihood of those samples under the model. That's the framework. And we're going to do that, in some cases, that likelihood is actually tractable to compute. And we're going to do a direct optimization of that likelihood. So that fits into these kinds of models. Normalizing flows fit in there, and the autoregressive models fit into there. And that's really their big advantage, is this tractability. On the other side, we have our variational autoencoder here, which is a form of density approximation here. And the problem there is that because they're invoking this latent variable, and the way they do it, you actually can't easily come up with a likelihood model that fits. And so what you end up doing is modeling a lower bound to that likelihood and then trying to optimize that, hoping that you're pushing up the likelihood at the same time. So that's the basic formalisms, and we'll go into that in more detail as we go along. So autoregressive generative models, basically the formula is this one, right? So we're going to express a joint probability distribution, and for our purposes, we need to think of X here as being very high dimensional. It's an image, right? So it could have thousands of dimensions. And we're going to, so this thing in general could be very complicated to describe, right? And so the way we're going to sort of piece it down to make it easier to model is we're going to decompose it using the product rule of probability, right? So we're going to decompose it into individual elements. So for thinking about images, these are going to be individual pixels conditioned on the other pixels. But we need an ordering to do this, right? We need an ordering over these elements in order to define this kind of product rule factorization. And so that's the one thing that's going to be a little bit weird about these models, in that if we're modeling things like images, we're going to need to define an ordering over these pixels. Now, for something like speech or language, that's easy, right? The temporal structure gives you a natural ordering. But for something like images, there is no natural ordering to pixels. So we're just going to arbitrarily define one. And almost always what we'll do is we're just going to start at the top left and sort of scan them like this, right? That's just the ordering we're going to pick. Nothing natural about that. Could have gone any ordering at all, but that's what we'll generally pick. Sorry?
Are you considering total orders?
Yes. Yeah. In general, yes. We're going to see models where well, it would be complicated to do sort of partial ordering. So in general, we're considering total orders. Yeah. You could get away with partial orders, but for our purposes here, we're going to do general orders. Yeah. So the pros of this kind of modeling approach is that it's tractable, right? If we can model these guys tractably, then we can combine them in this way to consider a joint distribution that can be very complicated in itself. So we're just doing this decomposition to actually render this thing much more tractable. And it can be easy to train. But the trick here is that, and conceptually it's easy to sample from, but the problem is that it's going to be very slow, right? Because sampling X1 here, it has to happen before we condition on it to sample X2. Right? So in this case, we're going to have to sample every pixel at a time. So sampling these models is slow, but we're going to see that we can actually make training very quick in these things. So essentially the modern autoregressive model, neural net-based autoregressive model that kind of started this whole thing again after the sort of the neural net winter through the 90s, or actually through the 2000s in this case, was NADE. So this is a work by Hugo Larochelle and Ian Murray. And what they do is, again, we're imposing an ordering over our x's here. So we have x1, x2, x3, x4. This is the ordering in which these will be processed. And then we're going to use a neural net to encode the conditional probabilities here. So we're just using a neural net, and the output of the neural net is the probability for that component. And we can see that our first component here is just P1, right? So think about binary values. This is what mostly NADE was used for. So this is just going to be P, some probability, heads, tails. It's arbitrary. It's just we're going to model it that way. Now, given that value of x1 here, though, we're going to be able to model probability of x2 given x1. Given the value of x1 and x2, here's what we're going to model the probability of x3. And you can see that the connectivity pattern in our neural net respects this structure of the joint probability given by this product rule, right? So in other words, you can see, for example, that x2 does not depend on either x2 or x3 or x4 or anything else that comes before. So that's the critical factor here. We're going to build a neural net structure that respects the essential structure of the product rule that we show here, right? Given the certain ordering that we've given it. And so for this, when we train this model, maximum likelihood training of this model, we're not sampling from this model when we train it, right? We're just doing maximum likelihood training, and what that means is that we're just going to take an example, say from our training set, and we're going to adjust our value p here to try to maximize the probability of x1, right? And then we're going to try to adjust the parameters of this thing using normal backprop, gradient-based backprop, to optimize or to maximize the probability of x2 given that x1, and we go along that way, right? So we're just maximizing the likelihood of the data given this kind of structure. And the important thing is we can do this in parallel, right, while we're training this model. We don't have to do this one at a time as I've described it. We can do it all at once because we have the training data. We have all of these at once. And this property, we call this teacher forcing because we're basically using the examples, we're conditioning on the actual ground truth values. But what that means, and this is really, really important for us, is that it allows us to train this model in parallel. That's really key. Because otherwise, it would be very, very slow to train these models. Now, the problem is that's great for training. When it comes time to actually generating samples from this model, you actually do need to do one at a time, right? So you need to, flip your coin here to generate a sample of x1, stick that here, and then push this up, and then sample from this distribution over x2, and then put that value here, push this through the model to get your x3, et cetera. So it takes lots of iterations through your neural net to actually get a sample across this joint probability. All right. So that's basically all I really want to say about NADE, other than the fact that when you apply this, it actually was a very high-performing model at the time, not necessarily for images, actually. So this is one of those models where, came out around the same time where these Boltzmann machines, or restricted Boltzmann machines that we mentioned earlier, were popular. And those models could actually generate better-looking images than this one. So this is the MNIST dataset. You saw some samples from it before in the last talk. Here we have essentially samples from that model. And you can see they're not very good samples, right? You could easily distinguish them from true samples from this distribution. I'm also showing the low-level features. People don't tend to show these anymore, but at the time it was fairly fashionable to show that. So there we go. This is just kind of showing the probabilities at every pixel point, and so this is actually those sample values. So you can kind of see that they're a little bit noisier. This is the fairer one to compare because almost everyone shows these probability values that are soft. So this is a value between 0 and 1. This is actually sampling from that. So there's like an incurred variance happening there. Now, why doesn't this look very good? Well, one reason why this probably doesn't look very good is because we're not using much of the structure of images in this model, right? We've just vectorized an image into this vector to give it an ordering. We've imposed some ordering on it, and then we've modeled it with a fully connected neural net, right? Which doesn't encode much of the information we know about images, and so it's not that surprising it doesn't work very well on images. But we could maybe do better, right? We can impose the kind of structure that we know exists in images by using something like a convolutional neural net. Right? So for those of you that know about convolutional neural, it's great. For those of you that don't, this is going to be a very, very brief introduction to convolutional neural nets. So the important features for us in a convolutional neural net is, the first thing is that we're going to preserve the two-dimensional topology of an image here. Rather than making it into a vector, we're preserving the 2D topology. And that we can interpret as being this 2D topology we have down here. Now this is going to be a hidden unit on top of it. Look, each one of these represents a hidden unit. And each one has partial connectivity to the layer below. Right? It only looks at what's called a receptive field. In this case, it's a 3x3 receptive field. So it's not looking at the whole image, it's only looking at part of the image. And actually, for every unit in this 2D topology, you can see that we're actually preserving the 2D topology of the image into our hidden unit structure here. And from here, we're actually sharing the parameters across. So the parameters that this guy's looking at this patch width, this guy's going to be looking at that patch width. It's the same parameters. So we're essentially convolving that feature detector across the whole image to come up with essentially what is a feature image in this space here. And we do that and that defines a feature map, and we do that for a whole bunch of different features, and we end up with a stack of feature maps. And then we can do the same thing again on top of that feature map. And so we sort of repeat this process over, and we can have stacks and stacks of these convolutional processes. And this is basically what gives you a convolutional neural net. So the problem is if we just sort of blindly think, oh, let's just throw a convolutional neural net onto what we've done with NADE, great, we're done, right? Well, the problem is that the convolutional structure, as I've described it here, doesn't actually respect that joint probability that the product rule gives you, that ordering that's required, right? Specifically, if we look at this guy right here, right, x1, which before should have no context. But if we see here, when this guy comes around, oh, it just came by. But anyway, it actually, the dependency that the ConvNet would give you includes this pixel, and this pixel, right? All pixels that happen after it, given the ordering we get. So there's something we have to add to this in order to make this thing respect the autoregressive structure that we need to define a proper joint probability distribution. And that's what's done, that's what's done with the pixel CNN model. So what they do, and this is again just two views of that same structure here, right? So this is our hidden unit structure, and you can see this as the input structure. But you could just as easily see this as some layer in the network, and this is the layer above it. It's identical, right? Because the same basic pattern repeats. And what we're going to do here is this box here would represent the normal receptive field for this unit in the layer above. And again, what we're saying is, given the ordering, and again, the ordering is going to go like this, right, from the top left corner here, scanning this way. And so what they're going to do is they're going to zero out all the values that come before this point in this given ordering that we have. So we still need to impose an ordering, but we can at least structure the model such that we respect this. We can both include some of the insights from convolutional neural nets, but we can also respect the ordering by imposing this mask convolution. So by zeroing out this value because it can't depend on itself and the other values around it. So that's the basic essentials of a convolutional, what's called the pixel CNN model. All right, so a little bit more, adding details to this. So this is basically the same structure here, right? So this is the pixel that we're looking at. The mask of the convolution looks like this. So this pixel, if we want to compute the value of this pixel at some layer above, it's going to depend on everything in blue, not the thing in red, and not anything here that's in white. All of those have been masked out. And the way we're going to model the output in this case, often what we're doing when we're modeling real value images is we just model the output as some real value, right? I say real value images. Of course, these things aren't actually real valued, right? They're discretized. And they actually, in this model, they actually modeled that discretization. So from value 0 to 255. So 256 different values. They actually will learn a histogram over that value for every particular pixel. Right, so that means they have to come up with 256 different output vectors to learn that pixel value. In fact, they go a little bit further than that because they do this for every color channel, and they model dependencies between the color channels. In particular, they model the red given the context. So the red doesn't have any dependence on that specific pixel, but the green value depends on the context and the value of the red pixel. And the blue value of the blue channel, let's say, depends on the context, the red pixel, and the green pixel, right? So pixel values, channels. And you can see here that these are just different trained up histograms that the model has learned for the output distribution for these different pixels. And you can see that they're actually quite different than the standard Gaussian distribution that we would have used normally in this case, right? So there's actually additional structure that they're capturing by using this histogram than they would have captured if they were just using a Gaussian. Yep?
Just a quick one. So in the dependencies, we actually make dependent. Is there any limit on how far behind we make the dependencies?
So we'll get into that in a second. In terms of you're asking about specifically about this context.
Yeah, like last pixel will have connection all the way from.
Right. Okay. We're going to get into that in a second. Well, let's try to. If I don't exactly answer your question, remind me again at the end. So this is basically the structure we saw before, and the way I mentioned to you before that the way we're going to implement that is with mask convolution, right? And there's actually a big advantage to using this structure because we can now essentially just plug this into a convolutional neural net, right? It's a particular structure of convolutional neural net in that it maintains the same dimensionality throughout the stack, right? Normally, a convnet loses spatial resolution as you go higher because in the end, all you want is a class label. But this is a special convolution, and it really just depends on some details of having, for example, if we go back here, having this kind of zero padding effect, right? It's a pretty easy structure that allows you to maintain the same dimensionality. But that's the kind of structure we see with these models. And if we do that, we can basically use just a standard convnet with this particular kind of masking so it zeroes out those values underneath. And what that allows us to do is basically just automatically use a convnet, train this thing, and all of the pixels we can train in parallel. We're using that same teacher forcing that we saw with NADE in the context of pixel CNN, and it trains really fast. It's just standard processing through a convnet, mind you, of a particular structure. But it trains very, very quickly, and for that, it is a very powerful model. Now, one detail, and this is going to get to that point, how much context do you have? Well, the context comes in, like our local receptive field is actually going to be quite small. And you can see that here in this blue pattern, right? But the point here is as we stack layers on top of that, the effective receptive field actually gets larger. This is just a property of convnets, that as you stack layers, the space in the input that a particular unit is sensitive to grows as you get deeper and deeper in the model. And you can kind of see this as sort of, this is the next layer up. For this pixel, right, at a second layer, it's sensitive to these values. At a third level, it's sensitive to these values. But you start to see another weird phenomenon here, which is this part right here. You see this blind spot that comes up. Now, I'm not going to go into exactly why using this kind of a masking structure gives you this blind spot. It's actually a pretty complicated thing. You sort of sit with pen and paper, and you can probably convince yourself after some amount of time. I'm not going to try to convince you of this right now, but it happens. It's a real effect. And the problem is it's a problem because as you get deeper and deeper, the convolutional structure should allow a unit here to be dependent upon all previous values, right, that respect our structure, meaning that the whole image that occurs to it before this point in the ordering that we've picked. But this blind spot is not allowing that to happen. You're not being allowed to depend on any of the points that kind of come out like this. So what the authors of the original Pixel CNN did to improve this is they actually introduced a kind of a slight modification where they're going to use a two-stack solution. One stack that looks just above here, so essentially it's like having two different kernels that they're using for the convolution or feature maps. One in this vertical stack and one in this horizontal stack. And they sort of maintain these two streams as you go through the layers. And doing that actually fixes this problem. It gets rid of this blind spot and improves the performance of these models. So again, I'm passing over this very quickly to actually see why this happens. It's useful to sort of pen and paper and sketch some of these examples out. I'm not going to do that for you. But I can show you the results, which is fairly impressive performance. So this was trained on a wide range of different kinds of images. I think this is ImageNet, but I'm not positive about that. And here is a case where they're actually conditioning on. So this is a case where they're building conditional models. So the model, while it's training, is aware of the class label. And then you can then go and say, generate images that look like sorrel horses. And it will generate images like this. At the time, these were actually very impressive images. Now, I have to say this because we're going to be talking over the course of a few different years here, and you're going to be able to see a difference from the publication date of the kind of quality that we're talking about. Some of it is just scale of models, but some of it is really we're improving our algorithms as well. So at the time, I can just say that at the time, these were reasonably close to state-of-the-art methods. I don't think they were quite as good as what you could get out of something like a GAN at that time, but they were pretty close. Another example, so conditioned on sandbar, you can get kind of these kinds of images. So I think what you can see in these kinds of images is that it gets the texture largely right. It's missing a little bit of global structure, right, which is pretty common with these kinds of models, actually. But so whole images might not make sense, but individual components of them really do make are quite believable. Even actually the children playing in the sand here seem at least recognizable. These are pretty low resolution, so yeah. Okay, and this is not going to spend much time on this, but this is a model. Again, it's autoregressive, it's tractable, so we can actually extract likelihood from these models. So what's being measured here is taking a test set from the same distribution from the training set, but these are examples that it wasn't trained on, and just seeing how well does it do on those samples. So you want those samples to be likely under the model. So we want to maximize likelihood or minimize negative log likelihood, right? So smaller numbers here are better because this is negative log likelihood, right? And we can see that we actually do very well. This is this gated pixel CNN. I forgot to mention that another innovation that they added with this improved CNN model beyond the stack is they actually added a special kind of gating mechanism through these two stacks, which turns out to be very, very effective. I don't know if they did any actual ablation studies to show the effect of just fixing the blind spot versus this added structure that they added with the gated thing. I don't believe they did, yeah?
So, were there any experiments in which, instead of having a horizontal and vertical stack, they had one stack propagated this way and the other this way, and that could get you dependencies from both directions?
You have to, well, you don't want dependencies from both directions for a generative model like this, right? Because you're still stuck, you cannot violate, if I go back, this basic framework, right? We still need an ordering, and to define a proper joint probability distribution, we can never have something depend on, like, it cannot be circular connections. Right? These are directed arcs like we see here, and we cannot have circular connections here, or else we simply are not defining a valid joint probability distribution. So we can't really do that. This actually comes up. This is a live issue when it comes to natural language modeling, because there are some models that are very high performing, but actually do exploit information from both halves. So they're not actually used as pure generative models, whereas other models only are directional, and then you can actually generate from them and use them as generative models. But they're both used, in that case, they're both used as for sort of downstream tasks like sentiment analysis or something like that. All right, so I'll skip back. All right, so that's it for applications to images. But what I want to talk about now just briefly is a model that applies the same basic technology to speech. Now, this speech is actually a really interesting domain because on the one hand, it's easier than images, right? For one, it's only one dimension as opposed to two dimensions. So we have a natural ordering again, right? Auto-associative models make sense again in the sense that you can just have the structure of the time define the ordering over elements of X as opposed to imposing an arbitrary ordering ourselves. But on the other hand, it has this property of having important structure happen at a wide range of scales, of temporal scales. And that's kind of shown in this graphic here, right? So what I'm showing you is basically, something stretching out in time, right? So we see right now we're looking at the low temporal structure of the carrier waves, right? If you don't model that properly, the sound ends up turning out to be very robotic compared to a natural sounding human, right? So our goal here is we're trying to model natural speech. We're trying to ultimately put in text and have somebody speaking come out of it. That's the goal with these kinds of models. And if you don't get the low-level details right, the very not high frequency, but the details at that time scale right, it sounds robotic. I don't know if you know the Battlestar Galactica, the Cylons on Battlestar Galactica. Anyway, it sounds like that. But speech signal, the words that are formed are happening more at a larger time scale, like this one, right? The carrier waves here are really conveying the information about the speech. So if you want the speech to be intelligible, you have to get that large scale time scale right as well. So the challenge with these kinds of models is, how do you do that? How do you get both time scales right? And so the way they did this is they used the same basic convolutional autoregressive structure as we saw with the pixel CNN, but they did something to it. So over here on the right, what I'm showing you is essentially, the left, regular convolutions, right? So this is what we saw with pixel CNN, right? Where we're just doing, in this case, the local receptive field is 2 pixels, and you can nicely see how as you go up in layers, the effective receptive field at this pixel, for example, is larger, right? It's 5 pixels. But of course, it's growing linearly, which isn't very good, right? If we want to get to very, very large timescales, lengths, or very large timescales, we'll need to have a very, very deep model, which is not practical for us. So instead, what the authors of WaveNet did, which is this model, which is, by the way, the same people that did the Pixel CNN, or at least the same first author, they introduced dilations to the convolutional model. And so the first layer is basically the same. So it's the same local structure being modeled at the first layer. But from there on, they're introducing spacings between the units that are going into the unit. So it's still 2 units at that scale, right? So this guy's still only looking at 2 units, but the spacing between those units is getting larger. And it's getting larger as you go up. So the effective receptive field of a unit at this level here is much, much larger. So doing that kind of spacing allows us to model much larger term structure in a reasonable number of layers. And that's going to allow us to generate pretty good sample quality in terms of synthesizing speech. Now, when we sample from this, so again, we get the same advantage here as we did with Pixel CNN. Training, we can train in parallel very, very fast. But sampling from this model, we're doing 1 sample at a time, right? And at high fidelity samples, we're doing that 16,000 times a second. That's expensive. So this is sort of how you would see this, right? So you sample this guy, then it goes back and feeds into the input, and you process that again, sample it again. So you can be a little bit clever about caching values, but fundamentally this is a slow process. And there's been a lot of work in improving this structure. But from a pure sound quality point of view, don't hear that? I don't know if you can turn that up. I have no idea how to turn that up. Volume? Oh, that's just, oh, okay. It's just on my computer here. All right, anyway, trust me, it's good. Yeah, so the sample quality is essentially really good under these models. And there's lots, you can look it up online later. There's lots of interesting samples you can get from these kinds of models. But the Achilles heel here is the sample is the slowness. So there's been lots of work going into speeding that up, which I'll not talk about from now on. Any questions on this point? Yeah.
Including these skips in the structure, still respect the initial assumption, the vectorization.
Yeah. Yeah, it does, right? Because it's all, in this case, like I said, it's what's called a causal structure, right? In the sense that the ordering is left to right. So any of these units are free to depend on anything over here. It just can't depend on something over here, which is like off it's not shown here. But yeah, it actually does. So you can see all the connections are always to the left or directly here. So in this case, you actually would not depend on this guy, right? This is actually a little bit wrong from a sample, you wouldn't want to depend on this guy if you're predicting that value. That's non-causal. But that's the only thing that's a bit off about this. But yes, you need to respect that structure. Any other questions on this before we change gears? All right. So now we're going to talk about a different modeling paradigm, normalizing flows. So we're essentially stepping away from autoregressive models, and we're getting on to these normalizing flows. So this is the basic idea of normalizing flows in one slide. So here what we have is we have 2 spaces. Now we're back to our latent variable space, but it's constrained in a way that makes it a little less interesting to me. But still, it's constrained to be the same dimensionality as the data space for very good reasons, which we'll get into. But the data space here, we imagine, is some complicated distribution. And what the goal is to map that to some simple distribution through what could be a very complicated mapping that's going to be parameterized by a neural net here, right? So some complicated data distribution pushed through a neural net to some simple distribution, which here is actually just a Gaussian distribution. So it's doing a warping into a space where we can now model this data simply. through this f of x here. Now what we're interested though, and when we do generative modeling, is we actually want to go back the other way. And the way we're going to do that is we're actually going to add some structure or constraints to our neural net here such that we can actually make it invertible. Now in general that's hard, right? Neural nets aren't really invertible or not easily so. But it turns out you can actually exploit the sort of multiple layered structure that they have, and as long as every single layer is invertible, and it's not so hard to propose examples of layers that are invertible. As long as you have that, then the whole deep neural network can be invertible, right? Just doing it one layer at a time. So it's a structure that actually lends itself fairly well to this kind of invertibility. But if we have that invertibility, now we have our generative model, right? We have some simple distribution that we can sample from in Z space, right? Gaussian distribution. So we sample our Z, then we push it through this new inverse neural net model here, and then we get an example in data space. Right? And that's how we can use these kinds of normalizing flows in the context of generative modeling. Now I should say, and I'll say it right now because we're going to see examples of this, these normalizing flows aren't just used as generative models. They absolutely can be, and they often are. But where I think they're almost more often used is actually to model more complicated distributions in things like variational autoencoders, which we'll talk about next, right? So there's different complicated distributions that we might need to model other than just the one going from X to Z. Specifically what I'm talking about is a model that goes from Z to X. And specifically what I'm talking about is a model that goes from X to Z. We might want a richer distribution in Z space than just a simple Gaussian distribution. And so we can actually employ these models in that context. But for our purposes and what we're going to be talking about now, we're just going to be thinking about these as just generative models in their own right. Okay. So how do we do this? Well, we can think of a simple transformation, right? It's on the one hand, we have this invertibility problem, which is going to be a real issue, and we need to deal with that. But there's actually another issue that comes up, which is just as important. And that's that if we imagine we have a model like this, a transformation here, like we can think of this as just a very simple transformation that takes X, multiplies it by 2, and now we have our Y, right? So we can think of this as like a very simple neural net, if you like. But that's perfectly invertible, no problem, right? Inverting this is simple, good, are we done? Well, not exactly, because what we're interested in doing is density modeling in this case. And what's in green here isn't a valid density because it's not normalized properly, right? Specifically, if this is a normalized Gaussian distribution, the integral under this Gaussian will be 2. So we lose control of that normalization. And so we need to correct for that. And in this case, the correction is simple. We just divide by 2, right? And we end up with another Gaussian distribution. In this case, all it is it's the same mean, just we've changed its variance. But this process needs to be generalized if we want to have more complicated mappings from our data space to our latent variable space. And the way we're going to do that is using the change of variable density formulation. So I don't want to spend too much time on this. But basically what we can do is, in the case where f is monotonically increasing, so we're just going to look at this line, right? So this is the case if it's monotonically decreasing. We can look at this one. But in this case, what we're interested in doing is expressing a probability density in the transform space y here, right? But we don't have that. What we have is a simple distribution in X. So we need to find a way to push in that distribution so that we actually can get the measure in X, have this distribution in Y formulated in terms of the distribution in X. So the way we're going to do that is just, by definition of what the density is, it's just the derivative of our cumulative density formula here, function here, and then we push that through Y. Well, what is Y? It's just the push forward of X here. And now what we can do is we can say, well, the probability here expressed in Y space, we can actually express that as the probability measure in X space, where we're just saying, well, now we're going to look at X as being less than the cumulative density function, less than or equal to the inverse function of Y. And so that just now, if we push this derivative through, that just gives us our density function in Y space. But we get this derivative here, right? This is the correction factor that we need, right? And now if we put this together with the case when f is monotonically decreasing, we end up with what is the change of variables formula here, which is just the absolute value of the partial derivative of f with respect to y, of the inverse f with respect to y. Okay, so that's fine. In one dimensions, this is actually relatively straightforward as long as we can compute both the inverse here and this derivative, no problem. It gets a little bit more complicated when we grow into higher dimensions, right? Because in general, what that formula in one dimension is, we can apply the same thing in higher dimensions. We don't have to go through the details, but it basically comes down to a determinate Jacobian computation, which for us, the important part is that it's an order M3, where M is the dimension of the input, right? So high dimensional images, this becomes problematic. So in moving forward, we're going to need to address the invertibility of the function. That's going to be an important part. And this is the second term. We need a practical way of computing this. So there's different strategies, and there's a whole host of literature on normalizing flows, and they're all coming up with different strategies for dealing with these two issues. Mainly this issue, actually. The invertibility usually is just defined by the structure of the model. So how we train these modelings, if we go back to the objective function, I'm expressing it here as a KL divergence between the true data distribution. So P of x here is the data distribution. P of y, now this is our simple prior, our Gaussian distribution in y space. And we want to think about this push forward as our actual model, our model that's going to transform from y into x. Right? This is our generative model, if you like. And that generative model, we can actually think about it in this formula as essentially coming down to, so when I talk about minimizing this KL divergence, this turns out to be exactly equivalent to maximizing likelihood. Formally, it's exactly the same. How can I show that to you? Well, if we sort of break this down, what we end up with here is a term. So this is our generative model. This is the thing we want to maximize the likelihood of. And if we think about where the parameters sit, our parameters are in F. So when we maximize this with respect to, when we compute the derivative of this with respect to the parameters, the only term this term just disappears, and the only term we're left with is an expectation with respect to the true data distribution that's given by our training examples, and then our gradient, which is negative here because we're minimizing the negative log likelihood. So that's just, but the point of this slide is really to say that this term here, we can kind of go through the expressions that we saw previously and come up with this term. So this is essentially our generative model that we want to maximize. So we've got just our forward model here, F, that's mapping from data space into our latent variable space, and then we've got this correction term. So that's basically what's being shown here. This is basically our model. So we want to maximize the likelihood of the pushing of the data such that it looks likely under our Gaussian distribution, and then we have to deal with this correction term. So when we think about these normalizing flows, and we've already talked about this, we've already talked about this, right? So we require an invertible architecture, and we need an efficient way to compute this change of variables formula, which is specifically this log determinant is the complicated part. So how do we do that? I mentioned already that there's a host of different ways of doing this. This is kind of a rough categorization or taxonomy of these different ways of going through it. I'm not going to go through all of these. I'm going to focus on two. I'm going to focus on this one right here, where it's basically, the strategy is essentially to say, well, we're going to use a residual connection. So we're going to modify f of x as just being x plus some low rank perturbation of it. So we can use this to ensure invertibility. And if this is low rank enough, then that determinant, that change of variables equation is relatively straightforward to compute. So and then on this side, we have these partial orderings. So we're actually going to exploit a little bit of the same notion that we had with our autoregressive model. And we're basically going to use partial orderings on and dependencies between variables to make the invertibility to allow us to do an invertible map by definition, but also to render that change of variables tractable as well. Okay, so a little bit in more detail. So the basic structure here is we're just going to use an f of x here that has this kind of simple form, right? So we have x, so we're just pushing x forward. It's like a residual connection. And then we have a single hidden unit here. So we've got an affine transformation that's to a scalar, and then we have this simple nonlinearity, which we're going to model as a tan h here, a hyperbolic tangent, and then we transform that again. So this structure with this kind of choke point allows this Jacobian determinant to be computed fairly straightforwardly. But it's a pretty low power kind of transformation, right? You're saying, take the same thing and modify it by this simple low rank, in fact, rank 1 transformation. And so you can kind of see that, this is Q0, this is before you apply any transformation. So this is an example of the kind of transformation you can apply with one of these transformations. But the power here is the same power we have with deep neural nets. It's stacking these things on top of one another. That's where we're going to get our expressivity. Because when we use two of these things on top of one another in succession, we start to get a more complicated expression. We use 10, we're able to model a lot more complexity as well. So it's by stacking these things where we get our modeling power. And here this is actually an example of showing the effect of stacking these models. You get better and better performance. So lower is better because it's a negative log likelihood. And this is, again, actually an application of these methods in the context of a VAE. Right? This isn't actually just a pure generative model in this context here. But they're using it in the inference process for a VAE here. Yeah. So you can do a little bit better than this. This rank 1 approximation is a pretty arduous thing, and you need quite a few of these to do fairly well. So you can actually generalize this somewhat. And this was done fairly recently by a group at actually Max Welling's group, I believe. So in this case, what they're doing is they're taking advantage of something called Sylvester's theorem to essentially allow you to generalize this somewhat. So instead of being a rank 1 transformation, it's a rank D transformation, where D is small enough that you can actually still do this determinate Jacobian reasonably tractably. But it gives you a lot more flexibility. And then, again, the strategy is to stack a bunch of these on top of one another. But allowing you to do a transformation that's more than just rank 1, gives you much better performance, as you can see here. So that's essentially what I'm showing right here. Right? So this model, and these are just different ways of essentially assuming that we maintain invertibility of the model. There's a few different choices for how to do that in this case, and they show that they can actually do fairly well. Okay, moving on to the partial order dependencies. Real simple how this kind of thing works. So this is the kind of ordering that we're talking about. We actually take X and we kind of block it into two different pieces. We're going to call this X1 and X2. And you can just take it and just push it into two different blocks. And then we do the same thing with our sort of next layer. And again, we're going to stack a bunch of these on top of one another. And what we can see, though, is by having a simple transformation where we're just adding some nonlinear function from X1 and passing that and combining it with X2 through this Y2 channel, we both ensure invertibility, because this transformation is perfectly invertible. And actually, the Jacobian determinant is just 1. It has the property that this thing is just trivially simple to compute. It gives us transformations a little bit like this, and if we stack enough of these on top of one another, we start to get some expressivity. We can do one better than this with a model called the real MVP by the same first author as NICE, which was the model I just showed you, and we just add a scaling term to the same model structure, right? Really simple, but it adds, again, for that first step of the operation, it adds a little bit more expressive power in what you can model. And again, stacking one on top of one of these, one on top of the other, starts to give you a bit more capacity in terms of in terms of the kinds of things that these kinds of models what they can do. And in this case, the Jacobian determinant is simply given by the product of the scaling factors here. Right, so really simple transformations. The structure of the model essentially is determined there to infer the invertibility as well as the tractability of the log determinant, the determinant Jacobian. Sorry. So what real MVP can do as a generative model, it can actually produce reasonably looking samples. Right. So it's actually pretty surprising that just stacking a bunch of transformations of this type, very simple transformations on top of one another, actually give you things that are pretty reasonable. And if you add a few more tricks to this, specifically how you split up the X, how you partition it into X1 and X2, you can be a little bit more clever about that, you can end up with a model like GLOW, which is close to the state-of-the-art model in this. The same basic technology of what we just showed you, right? Exactly the same. It's just a few extra tricks now and just a few, but yeah, it's a bit more complicated to explain how it works, but really, fundamentally, this model is using the same technology as real MVP that we just described. So these are very simple models, but deployed at scale can actually give you pretty reasonable things. One thing I want to note about these are actually like they actually do kind of glow. The reason for this, it's not just because it's a data set of celebrities. It's partly that, but they're actually, to make this model work, they're not actually sampling from the training distribution here as you do with a model something like, or getting samples that reflect the full training distribution. It's more like they're looking for local modes in the model distribution. So they actually reduce the entropy of the samples here. If you were actually just to draw samples from this model as you would with something like a GAN model, they don't look nearly as good. But they can still sort of do this local entropy reduction, and they end up getting very good looking samples. And over here we have bedroom scenes over there. Okay, so that's normalizing flows. Sailed over it very, very quickly, but there's a lot of interesting literature there. This is not a topic that I used to cover very much, but it's becoming more and more important, especially with the results like we see with GLOW. I think it's a really important element to be aware of. And especially they're very powerful for injecting into different places in models, like the variational autoencoder, which is what we'll cover next. And how are we doing for time? Not too bad. All right. Oops. So, variational autoencoders. So this is a model or a piece of work that has, actually, before I go on, is there any questions? Are there any questions about normalizing flows other than what we've had so far? No? Okay. So variational autoencoders was actually invented by two different groups, one at DeepMind, one at the University of Amsterdam at around the same time. Yeah, the name really is inspired by the one by Kingma and Welling, but it's essentially the same model inspired by at the same time. Yeah. Right. So I mentioned before when we talked about normalizing flows that these are latent variable models, but not ones that I really feel very close to or that I really liked. And the reason for that is because of all of these constraints that we have, right? To ensure invertibility, well, actually that one all by itself is all you need. To ensure invertibility in general, the latent variable space and the data space have to be of the same dimensionality, right? Which from my point of view and from the point of view of this image really destroys what is most powerful about latent variables. Latent variables, what you want them to do is capture the true underlying structure in the data, right? The true variations in the data, and not necessarily. We don't think that variation in the data fills the data space. In other words, we ought to be able to express for something like natural images the variability in natural images in a space that's much, much smaller than you would need to express the natural image. Right? We kind of know this, right, in the sense that we can make the resolution of the natural image as large as we want, and that doesn't change the underlying semantics of the scene, right? So there has to be some underlying distribution that doesn't grow as the resolution of the image grows. And that's what we're seeing, we think of when we think about these latent variables. That's what we hope that these latent variables will capture. And in those normalizing flow type models, we're not going to get that kind of structure, right? Because it's imposed to be the same dimensionality of the data. That's why we have an interest in models like the variational autoencoder, which really takes this idea to heart. All right, so this is kind of the spirit of this kind of model. And really this kind of point of view precedes the variational autoencoder by quite some amount of time. The idea here is that we have, and the spirit of this, we have some lower dimensional Z that captures this variation. And then we want to think about generative models as being sampling from this in maybe some simple distribution. So in that way, it's like normalizing flow. So we have some simple distribution in this space. And then we sample from that and then push that sample through G, and that underlying distribution here, that underlying space, reflects the manifold of where the data lies in the true data space here, right? So we're making an assumption here, right, that the data lies on a lower dimensional manifold. But for many, many cases, this seems to be a reasonable assumption to be made, especially when it comes to things like natural images. So this is an example kind of in 2D representing the kind of idea that we imagine, right? So the data here clearly has structure. It doesn't fill this whole space. And we can actually describe an underlying manifold, which every data point is kind of a perturbed example from that underlying manifold. That's kind of the way we can imagine what the data looks like. And our goal here is to, with these latent variables, is to capture that underlying manifold. Okay, so the problem is that when we have these kinds of models, learning them is not going to be very simple. So again, we can express what we want here in a bit more mathematical framework. We can express a probability distribution in X as being defined through some joint probability distribution. And really what that is that's defined through this kind of factorization. So we have our simple distribution P of Z, right? This is our Gaussian distribution, let's say. And then we have our generative model, which is capturing the mapping from Z into X, right? This is our G here that maps from our simple distribution here into our complicated distribution. And we want to sort of have these Zs actually decouple sort of meaningful pieces of information about the data, right? So we want Z2 here, for example, to maybe reflect something independent about the way our data varies compared to Z1. And it's a big ask, but we're going to want this from our model, that it not only learns to generate realistic-looking samples, but that it actually captures some underlying trends in those models along these latent variables. So the way we're going to do that, since I'm talking about it in this talk, we're going to actually think about this G being parameterized by a neural net, right? So we're going to start with a sample from some simple distribution. Again, we're almost always going to be considering a Gaussian distribution, and we're pushing that through into our data space through a neural net. And I show you a fully connected model here, but really for images, you should be thinking about this being a convolutional neural net, because it almost always will be. However, in this case, because we're not keeping the same size, we actually have to sort of do that normal process with a ConvNet where you go from a 2D topology into sort of a fully connected unit. We're actually going to do that in reverse, right? We go from this fully connected structure into a 2D topology by just imposing structure at some point. It feels very arbitrary at that point, but then you sort of keep going with the same kind of growth in structure. Like I said, it's sort of the same process, but in reverse, as you see with a standard ConvNet for discriminative task. Okay, now I talked about training these models a little bit. What we're interested in doing is maximizing the likelihood of the data, right? We have this joint probability with X and Z, and we're invoking these latent variables, but the problem is they're latent, right? Which means we don't know what they are, they don't come with the data, we don't have pairs of X and Z, all we get are X. And so the only sensible objective we can do when we're training these models is to optimize or maximize the likelihood of X. So the way we're going to think about doing that is essentially expressing the way we've parameterized these models, right? This is our neural net here, and this is our simple distribution. And so we want to maximize this log probability of X. We essentially have a formula like this, right? So this is log probability of X we can express in this form, right? If Z is real valued, we need to integrate over it. In other words, we're marginalizing out our latent variable Z, right? So this is what we would do. Now, the problem is this operation, if these things were discrete, this would be the form we would have. But in the case of variational autoencoders, Z is typically or almost always real valued. In fact, for variational autoencoders, it is always real valued. And so we're really dealing with this expression over here. And the problem is this is just not tractable, right? We're doing this integral is actually not tractable. So what we need to do is come up with an alternative to this to train these models. And this is that thing I was telling you about early at the very beginning of this talk, that with these models, we can't actually express a tractable density. We actually have to approximate it. This is where that approximation comes in. Because what we're going to do is we're going to actually take we're going to say that, well, if we knew Z, then it's actually much more straightforward, because dealing with pairs of these examples, it's actually really easy. If we just go back here, right? We have a neural net. If we had pairs of Z and X together, well, now we're just in the space where we know how to train neural nets, right? We have input-output mappings, backprop through, we're good. That's what we don't have the Z that corresponds to the X. We have the distribution that Z comes from, but what we need are paired examples of Z and X to train this model. And that we don't have. So how are we going to do that? Well, we're going to use this essentially expected complete data likelihood expression. So we're taking some expectation with respect to some Q of this log joint probability distribution. And we're going to add meaning to that in a second of what that actually is and why we're going to do that. But before we do that, we need to think about where Q is going to come from. Right? So we have some approximate distribution for Q. And what's suppressed here is that really this is going to be per X, right? So you should really think about this as Q of Z given a particular X, because that's what we need. We need the Z that goes with a particular X. And so there's kind of two different ways of doing this in general. One is you can just use Monte Carlo sampling, so you sample from a bunch of Zs and sort of push it through in our neural net into X, and we can kind of do an optimization that way. Or we can use variational inference. And that's actually a very standard way of doing this long before we sort of got into this with deep learning. But the variational autoencoder is actually going to apply this in a very specific way. Before we get into that, I'm just going to define, we talked about KL divergence earlier, but I didn't really define it for you very particularly. So this is actually the definition of KL divergence, but between P and Q. Now the thing about KL divergence that's important to know is that it's actually an asymmetric divergence, right? So it's not formally a distance measure. It's a divergence, but the important thing for our purposes is that you end up with a very different answer if it's KLPQ versus KLQP. And variational methods belong to this category here. And it's very important that they do because this Q here is usually going to be something that's tractable, and it needs to be in order for this expectation to be tractable. So this is the kind of KL we're using. I haven't showed you really how we're using this yet, but it's just important to know that this is the one we'll be talking about. And the way it's used, you can see that these are essentially fits to these distributions. So in blue here we have the approximating distribution for our purpose Q of Z. And in P is like the true data distribution. So this would be the true posterior of Z given X, let's say. And this would be an approximating posterior of Z given X. And here you can see this is what would happen. If this was bimodal in this case, this directionality of the KL will actually try to fit both modes. Whereas this direction actually fits only one mode. So this actually has real consequences when it comes to these kinds of models. But we're not really going to touch on that much further. Okay, so I mentioned this piece right here that we're actually going to be modeling that way. I'm not going to derive this expression for you, but it's actually really straightforward to do. It's just a few lines of math. Normally I do, but I'm lacking time to do it here. But we can express the log probability on X as equal to something that we're calling the evidence lower bound here. And this piece right here just ends up looking like this, right? So it looks a lot like a KL divergence, so it's different in detail, because this is the complete data likelihood here, right? So we're taking an expectation with respect to this approximating posterior distribution here of the ratio of the log probability and that approximating distribution, right? So this is the complete data here, and we're essentially saying that in this case that it's basically like if this were the actual exact distribution, the actual P of Z given X, then this thing collapses and it just amounts to being P of X here, right? So the degree to which this differs from the true posterior is actually given exactly by this KL divergence here. And the way to think about that is we have this lower bound here. This is the thing, this is given by this term right here, the evidence lower bound. And then we have up here the log likelihood on the data, and the difference between those two is exactly this KL divergence. Now, the important point of all this is just that when we're optimizing in the variational autoencoder, we're going to be optimizing this thing because it's actually going to be tractable for us to do. We're going to be pushing this up. But our goal in doing that is actually to be optimizing this quantity here. Right? That's all we basically need to know from that. Okay, so again, now this is going to become our new objective function. This evidence lower bound is the objective function for our variational autoencoder. And what we can see here is, we're taking this term and we're just going to be decomposing it into these two pieces, rearranging terms a little bit. We end up with this term here, which we decompose into yet another KL divergence. But this is an interesting one because it's between the approximating posterior and the actual underlying prior distribution on Z. And then this term, which is taking samples, an expectation with respect to Z here of X here. We're trying to maximize the likelihood of X given our approximating Z. So why this is interesting is if we think about an autoencoder now, this term here is essentially exactly the kind of term that you have in an autoencoder. Because what we're doing is we're taking this expectation, we're taking an X, pushing it through an encoder, which is basically what our Q theta is, our Q of Z is, an encoder. We can think about sampling from this thing, and then condition on those samples, we're trying to reconstruct X, or in other words, maximizing the likelihood. So this ends up being just like an autoencoder reconstruction term, hence the name variational autoencoder. But we add this extra term here, which we don't normally see with just a standard autoencoder. And this is really a regularization term. This is essentially enforcing that this Q respects something about this prior. Now, I don't want you to think about it as, when this reaches its optimum, this Q is going to equal this prior. That's actually a very undesirable point, right? Because what that means is that there'd be no information about X at all in this posterior distribution, because it would just match the prior. That's not what we want. But it's a regularizing term, so it's just like any kind of regularizer, right? You want it to have an influence on the optimization process, but not necessarily drive it to the 0 point of the regularization. So now the question is, so the VAE approach is we're going to introduce an inference machine, this Q here, this encoder I've called it, that learns to approximate the posterior through this objective function. And so where does this thing come from? What is this inference machine? Well, we're going to imagine it's another neural net, right? So it's our F neural net here. So we have X mapping through to Z. We've got a neural net that's approximating this posterior distribution. Well, actually approximating the true posterior distribution. And then we have our generative model, G, that takes a sample from Z and pushes it through to X. And what's really interesting is we have an objective function that will train both of these models simultaneously, right? Because both of models appear here. Now, the trick is we need one more thing. We need one trick to make this work. And what the trick is actually called the reparameterization trick. And the reason is because if we think about this is a stochastic variable. We want to train this model with backpropagation through the whole thing. Right? We want to start with an X here, encode it, decode it, do reconstruction error, and then backpropagate that error all the way through. That's what we want. But to do that, and that's going to train the encoder, right, to match this decoder or generative model. But in order to make that work, we need to make this. We need to figure out how to backprop through this stochastic variable here. So the way we're going to do that is with this reparameterization trick. So we're going to assume that Z is some form that can be expressed like this, right? So if Z were Gaussian distributed, we'd have no problems, which is what we're going to assume for our purposes here. So now we're going to just have our encoder parameterize some function for the mean and some function for the variance, and then we're going to just have this term here, which is just a sample from a standard Gaussian, right, that has no parameters in it. And then so we're expressing Z as this combination. And what this allows us to do is express Z as some arbitrary Gaussian distribution, right? Well, arbitrary in the sense of it. We assume that the dimensions are independent here. So this is an element-wise operation. But otherwise, it's an arbitrary Gaussian. But we're drawing samples from the standard Gaussian. And the variance from that is parameterized through our encoder network. So now what's nice about this is we can actually backpropagate through this process and backpropagate into the mean and the variance terms, right? We don't backpropagate through that epsilon, but that's okay. We don't need to. So we forward propagate from the data all the way through to X, and then we backpropagate the error all the way, again, through those mean and variance terms here. That allows us to train this model very effectively. And that's the piece that was really missing from this before. So before this model came along, people knew that we could express, encoders with neural nets, decoders with neural nets, but how to actually get them to train together was actually a missing piece. And using this parameterization trick, this reparameterization trick, was really crucial to make backprop happen in that way, and allowed us to actually train better models than we've had before. So I say better models. This is a kind of sample that came out that you can get from a vanilla VAE model. It's not particularly great at generating good-looking samples, but we can actually add some pieces which will make this a much better generative model. And we're going to talk about that with the time I have left, which is not very much, but it should be enough. So in this case, I want to show you one more thing before we move on, which is I promised you that we would disentangle, or at least we had a goal that these latent variables would somehow disentangle factors of variation in the input. So this is, to some degree, we're getting that with a variational autoencoder, and that's what's being plotted here, right? So in a case like MNIST, it's not very clear that that's really happening, right? But in the case of this Frey faces data set, which is a data set, a relatively small data set made up entirely of faces of Brendan Frey here, with different facial expressions and different poses, right? His face pose. And what we can see is that when we encode this into 2 dimensions, the pose and the facial expression get disentangled from each other, right? This dimension, Z1, is encoding pose, and Z2 is encoding the facial expression. Just realized something. There we go. Damn it, no. Didn't work. All right. Yeah, so I guess I'll take this back. So we actually do see, to some extent, this kind of disentangling. I'm going to skip over this part because I don't think it's that too essential, but much work has gone into improving what I've shown you is the very basic variational autoencoder, but there's been a great deal of work that has gone into improving this model. And there's a few different ways of thinking about how to do it. One way to think about this is there's a few different sources of error, right? I didn't talk about this much, but there's something called the amortization gap, which is essentially we're incurring an error by predicting this value of our approximating distribution. Compared to the way variational methods usually work, you're actually doing an optimization for every x, right? So within the family of distributions you're considering, you actually have a value that you're optimizing. And so you can imagine that you can incur an error due to the fact that you're using a neural net to predict that value as opposed to just doing a proper optimization within that family. And then you actually have an error due to the approximation that you're making there as well. So both of these two things are sources of error, the actual approximation family that you're considering. Anyway, and there's different strategies you can go into to improving these. But I want to skip ahead because I want to talk about a particular model which combines this variational autoencoder with the pixel CNN model that we talked about earlier. And it's the pixel VAE model, not a very original name. This is work that we did about 2 years ago now. So here what we're doing is we're trying to take advantage of the fact that we want a hierarchical model, right? So we're not just using a single layer of latent variables and an input. We're actually thinking about modeling multiple layers of latent variables. But we want to model the structure of the latent variables in a much more rich way than we can get from a standard VAE model, right? So a standard VAE model, we're making these independent Gaussian approximations, right, in order to do that. Here what we're doing is we're actually, instead of using just a single Gaussian, independent Gaussian, we're actually going to stick a pixel CNN model that we've talked about earlier in between every place, in between these different values of the hidden units. So here again, our goal is to model images. And so we're actually, our Z1 here is, and all the way up to ZL. ZL is actually fully connected, so you can think of that as a vector. But all of these other layers of latent variables actually have the 2D topology. And we want to be able to model that 2D topology. And so we're going to do that with these pixel CNNs at all of these different layers. And so it's actually relatively straightforward conceptually to integrate the two models together. So the objective function that just becomes, we have the standard reconstruction error, and now we have our sort of a branch that's going to approximate our distributions over these latent variables for given an x. And now on this side, we've got these pixel CNN models. It's modeling a complicated prior distribution. So you can add complexity here, or you can add it here. In this case, we're sort of adding it along this pipeline here with the pixel CNN model. And so we're actually expressing now our objective function is essentially the combination of the KL divergence at every layer between our encoder and our decoder, and then the reconstruction term on the bottom. Right? So that's just the model structure that we have. This is kind of just a highlight of how this thing would look. So we have images, we have our encoder up to Z. So we have our latent variables, but again, keep in mind that these are going to actually have structure to them in the sense of a topology. We go through a decoder, and then we have these pixel CNN layers here, which model the input. So this pipeline occurs essentially at every one of these layers. Well, we can pass over it. Anyway, the point I really want to make when showing you this model is that we're kind of combining the two different strengths of these two different types of models. VAEs give very blurry outputs, right? But they do something about preserving the global structure of the image. In this case, that's really hard to see. But there is actually global structure that's kind of being preserved. It's kind of all that's being preserved in this is actually the global structure. The pixel CNN model does a really good job capturing local textures, but it's not great at capturing global structure. So we're trying to combine these two models together to get reasonable looking samples that preserve something about the local texture and the global structure. And we sort of get that with this pixel VAE model. This is a low resolution version, but we actually get reasonable looking samples. These are unconditional sample, actually. It's just on the bedroom scene. So we're able to get reasonable samples from that. And reasonable looking things from samples from ImageNet at the time. We're not seeing objects. We're not capturing global characteristics here, but it's actually very challenging to do that in an undirected way with the pixel VAE model. Last thing I want to show you guys is that in this pixel VAE models, we can actually look at what the different layers are encoding, right? I mentioned that there's these multiple layers of latent variables. We can think about just moving them a little bit and seeing what each one and looking at the result of that process and see what's being encoded at each one of these different layers. So first of all, if we just think about the lowest level here, it's barely perceptible what that lowest level is modeling here. There's not a lot of variability across these. So our lowest level pixel CNN model isn't actually capturing very much variability in the image. But as we move up, as we vary this sort of mid-level model, we can see that the basic shape of the room doesn't change very much, but sort of colors are changing somewhat. Like the bed sheet is sort of varying in color. That's kind of, in this case, patterns on the rug are changing, but the basic shape doesn't change very much. As we go up and we start modifying top layers, sort of what's being shown here is that everything else is being fixed, and we're just sort of randomly sampling different values at the top layer and seeing how it changes. And here we see actually pretty gross changes, like colors can change pretty dramatically, whole room configurations can change. And so I hope we can see sort of the different layers of this model are actually sort of modeling different pieces of the problem. Right. So I'm going to basically stop there just to say that we can go further with these kinds of models, incorporating different kind of structures. We can apply them to temporal sequences, and we can get actually models of videos with VAE-based models of videos that actually look reasonably well. This is just a different competitor model. This is our hierarchical model that I showed here. And what we found really important was to actually add lots of capacity connecting these different layers to each other. So add richness in terms of modeling the latent variable distributions. And if we do that, we actually get reasonable looking generative models for video. Video is actually super hard to model compared to images. It's surprisingly difficult, but we're getting slowly better. And I'll show you tomorrow an example of a GAN-based model that came out this summer that actually is really, really good for video. Okay, and I think that's all I wanted to show you. So just overview of what we covered. We covered autoregressive models, pixel CNN, well, first NADE, pixel CNN, WaveNet. Then we covered latent variable models, normalizing flows, and variational autoencoders. And tomorrow we're going to maybe slow it down a bit because we're only going to be talking about generative adversarial networks. All right, thanks. Yeah.
You don't know the answer, but if you look at full VA, the encoder and decoder, what is the expectation if the encoder we give an input that is not from the training distribution? It's like an out distribution sample. What do we expect that the output of the input is?
Okay, so you're saying we have a VA model, we trained it on some data, and now we're going to give that model on input to the encoder something that is outside that training distribution.
Right, so let's say we train it on endless, and that we give it a far image.
Right.
What would we expect of the output?
I think you could expect anything, right? You've not trained on that that example. So it could output pretty much anything. It could interpret that as it could put that into the distribution of the MNIST examples, and so it would actually like if it's arbitrarily far from the distribution that you've trained on, you wouldn't expect it to give you anything sensible at all. And what it could give you is something sensible from the training distribution, from the this model by the training distribution. So you could put a horse in there, and it's going to give you 2 in reconstruction fact. That's a possibility. But I think more likely what it's going to do is if you put a horse in there is it's going to give you something that's just far from the original training distribution, and it's going to generate just garbage.
So I guess the question was motivated by, does the encoder always end up mapping into the sort of trained?
It's trained to do so, but it's trained to do so subject to the training distribution. So as soon as you break that, all bets are off. There's no guarantee that the model is going to map everything. In fact, it's not. It's just not trained to do that. It's not trained to map everything to the prior distribution. So yeah, I think it could, right? Just because again, all bets are off what it's going to map to, but more likely it's going to map to something outside that training distribution.
Would it be that it maps to sort of the mean and covariance that is outside the learning?
Yeah, that would be my guess.
Yes, thank you.